The Oort cloud is not empty. James Webb just proved it. For nearly 80 years, the outer edge of our solar system has lived almost entirely inside equations. A vast, theoretical shell of frozen debris wrapped around the Sun, sitting somewhere between 2,000 and 100,000 times the distance from the Earth to the Sun. We could not see it. We could not measure it directly. We could only infer it had to be there, because the comets that occasionally fell into the inner solar system had to come from somewhere. Now, for the first time in history, a telescope sensitive enough to register the faintest whispers of infrared light has turned its mirror outward, toward that frozen frontier. And what it is finding is not the silent void we expected. This is the story of how the most distant region of our own solar system stopped being a guess and started becoming a place. In 1950, a Dutch astronomer named Jan Oort was studying the orbits of long-period comets, the kind that swing past the Sun once every few thousand years and then vanish back into the dark. He noticed something strange. These comets were not coming from any specific direction. They were arriving from every possible angle in the sky, as if they were being knocked loose from a sphere that completely surrounded our solar system. Oort proposed a reservoir of icy bodies that had been ejected to the outer edges billions of years ago by gravitational slingshots from the giant planets. A graveyard of leftovers from the birth of the planets. A frozen library of the materials that built everything we know. The problem was, nobody had ever seen it. For 70 years, the Oort cloud was the most important place in our solar system that no human eye had ever observed. The inner edge sits about 186 billion miles from the Sun. The outer edge stretches out to a staggering 9.3 trillion miles, more than a third of the way to the nearest star. If you could climb into a car at 60 miles per hour and drive without ever stopping, it would take you more than 350,000 years just to reach the inner boundary. To cross the outer edge, you would need over 17 million years of unbroken driving. There is no warmth out there. The light from the Sun has thinned to almost nothing. Anyone standing on a body inside the cloud would look up and see our star as just another point of light in the sky, barely brighter than the ones around it. The temperature hovers just a few degrees above absolute zero, the coldest temperature physically possible in this universe. Picture standing on the surface of one of these distant bodies. You would barely weigh anything. The object itself might be only a few miles across, so gravity would barely register against your boots. You could jump and stay aloft for minutes at a time before drifting back down. The ground beneath you would not be rock, it would be ice, compacted into something harder than steel by billions of years of vacuum and cold. The sky overhead would be black, deeper than any night sky on Earth, scattered with stars so sharp and unwavering they would look like pinpricks cut through a velvet curtain. The Sun would still be there, somewhere in the constellation of your choosing, but only as a slightly brighter star. You would have to search to find it. The silence would be absolute. No wind, no air, nothing to carry sound, nothing to carry warmth. Just you, the ice, and a long, slow orbit, taking longer than the entire history of human civilization to complete a single lap around the Sun. This is the place James Webb just looked into. Hubble could not see it. The great ground-based telescopes could not see it. Spitzer, the previous infrared space telescope, could not see it. The objects in the Oort cloud are far too cold, far too small, and far too distant to be picked up by any instrument we had ever built. For decades, astronomers studied the cloud the only way they could, by waiting. Waiting for one of the cloud's residents to be jostled loose by a passing star or a galactic tide, and to fall inward toward the Sun, where the warmth could finally make it visible. A passive science, listening for messages that arrived once every few thousand years from a place we could only guess at. The James Webb Space Telescope was not built for this. It was built to look at the earliest galaxies in the universe, to peer into the dust clouds where new stars are being born, to analyze the atmospheres of planets orbiting other suns. The same instruments that can detect the faint thermal glow of a planet 700 light-years away can also detect the faint thermal glow of a chunk of ice drifting in our own backyard. The difference is, our own backyard is a place we had barely begun to map. Webb's mirror spans over 21 feet across. Its detectors are cooled to extreme temperatures, in some cases just a few degrees above absolute zero, so the telescope's own heat does not drown out the signals it is hunting for. And starting in late 2022, those detectors locked onto something that had no business being where it was, doing what it was doing. Its name is Comet C/2014 UN 271. Most people call it Bernardinelli-Bernstein, after the two University of Pennsylvania researchers who first spotted it in archived survey data in 2021. Pedro Bernardinelli was a graduate student at the time, working with images from the Dark Energy Survey, a project designed to study how the universe was expanding. The survey had taken hundreds of thousands of pictures of the southern sky over 6 years. Buried in those images, the team found a faint object that nobody had identified before. It was visible only because the survey was so deep and so wide that it accidentally caught a comet most other telescopes would have missed. As they tracked its motion across the archived photos, they realized it had been getting closer for years. When they ran the orbital calculations, the numbers came back wrong. Not technically wrong, but wrong in a way that did not fit anything anybody had expected. The nucleus of Bernardinelli-Bernstein, the solid core at the heart of the comet, is roughly 85 miles across. That is not a typo. 85 miles. Hale-Bopp, the bright comet that lit up the sky in 1997 and was considered enormous at the time, had a nucleus around 25 miles wide. Halley's comet has a nucleus barely 9 miles across. Bernardinelli-Bernstein dwarfs every other known comet in the solar system. It is bigger than most asteroids in the asteroid belt. If you set one end of it down in lower Manhattan, the other end would reach Philadelphia. A single object falling toward the sun from the Oort cloud, the size of a small American state. If something this big exists out there, it almost certainly is not alone. When Webb turned its mirror on this object, the comet was still over 1.2 billion miles from the sun, well outside Saturn's orbit. It was so cold that water ice should not have been sublimating. There should have been almost no activity at all. Instead, Webb detected something unexpected. Carbon dioxide outgassing from the nucleus. The ice was bleeding. Slowly, quietly, in the deep cold beyond Saturn, the comet was venting frozen gases that had been locked away for over 4 billion years. Gases that were present when the solar system was forming. Gases we have never been able to sample directly. Webb was not just looking at a comet. It was reading a chemistry record older than anything in the inner solar system. And it raised a question that nobody has a clean answer for. If Bernardinelli-Bernstein formed in the outer solar system and got slingshotted into the Oort cloud billions of years ago, how did an object this large survive the ejection at all? Most theoretical models predict that objects scattered outward by Jupiter and the other giants would be small chunks of ice, boulders mostly. The math did not allow for mountain-sized comets to be common out there. Webb's observations do not just describe one object. They describe a whole population that was not supposed to exist. Caleb Scharf, an astrobiologist at NASA Ames, has been arguing for years that we vastly underestimate the complexity of the outer solar system. The bodies out there, he points out, are not just leftover construction debris. They are time capsules, frozen, preserved, untouched by the heat and radiation that have altered everything closer to the Sun. If you want to know what the chemistry of the early solar system was actually like, you do not dig into Mars. Mars has been baked and scoured. You do not look at the Moon. The Moon is a battered shell. You look at the bodies that have been sitting in the deep freeze for 4.5 billion years, doing absolutely nothing. That is exactly what the Oort cloud is. And that is what Webb is now able to see. One icy messenger at a time. A few months later, Webb pointed at another long-period comet, Comet C/2017 K2 Pan-STARRS. This one had been discovered in 2017 by the Pan-STARRS Survey Telescope in Hawaii, and it had already become famous in the astronomy community for being active at distances where no comet should be active. Webb's spectrometer broke the gas surrounding the comet's nucleus apart into its component fingerprints, and what came back was a chemical signature nobody had ever recorded in this kind of detail before. Carbon monoxide, carbon dioxide, water ice. Organic compounds that suggest the building blocks of biology were already present in the cloud that became our solar system. These molecules were not made on Earth. They were made out there, in the darkness, before our planet existed. The chemistry Webb is finding in these long-period comets does not match the molecular fingerprint of the comets that come from the Kuiper Belt, the closer reservoir of icy bodies just outside Neptune's orbit. The Oort cloud comets carry a different signature, more carbon-rich, more volatile, older in some sense, even though all of these objects formed during the same chaotic era. This means the Oort cloud is not just a passive storage container. It is a record of a different stage in the solar system's birth, a composition that the inner solar system has long since erased. We are no longer studying a generic frozen graveyard. We are studying a stratified, layered, chemically complex region that holds information no other place in the solar system can give us. Stay with me, because what came next forced astronomers to reconsider where the cloud's material actually came from in the first place. The current best estimates for the number of objects in the Oort cloud range from a few trillion to several trillion individual bodies. That is not an exaggeration. Trillions. The total mass of all that frozen material is somewhere between 3 and 20 times the mass of the Earth, spread across a volume so enormous that the average distance between any two objects is millions of miles. If you were standing on one of them, you would almost certainly never see another one with your naked eye. The cloud is empty in the sense that there is nothing nearby. It is full in the sense that there is something almost everywhere. Imagine taking every grain of sand on every beach on every continent of Earth and scattering them evenly through a sphere reaching halfway to the nearest star. That is roughly the density of the Oort cloud, a vast three-dimensional fog of frozen rock and ice slowly orbiting our Sun on timescales of millions of years. Webb cannot see the cloud as a whole. The objects are too small, too cold, too far apart. What Webb can do is catch the individuals as they fall inward, picked off one at a time by the gravitational tugs of passing stars or galactic tides. Each comet that swings into the inner solar system is a single grain of sand from that distant beach falling into our view. Every one of them tells us something about the population it came from. There is one object that has already given us a hint of what the inner edge of the Oort cloud might look like, and it was found 2 decades before Webb existed. In 2003, a team led by the astronomer Mike Brown at Caltech discovered a small reddish world they named Sedna. Sedna's orbit takes it from about 76 times the Earth-Sun distance at its closest approach, all the way out to nearly 940 times that distance at its farthest. A single orbit around the Sun takes Sedna over 11,000 years. It is too far out to be a normal Kuiper Belt object. It is too close in to be from the main Oort cloud. Many astronomers now believe Sedna is a member of the inner Oort cloud, a region we had only theorized about until Sedna's discovery made it real. It is the first inner Oort cloud body we have ever found, and we found it almost by accident. Webb has been observing Sedna and a handful of similar bodies, building a chemical profile of objects that may represent the boundary between the inner solar system and the deep frozen archive beyond. Astronomers like Karen Meech at the University of Hawaii are now compiling Webb observations of multiple long-period comets into broader comparative studies. The objects falling from the Oort cloud are not uniform. Some are old, original members that have never approached the Sun before. Some are dynamically new, freshly disturbed from the cloud and falling for the first time. Their composition varies in ways that suggest the cloud itself has structure. There may be regions richer in carbon, regions richer in water, possibly even regions seeded by interstellar material captured during the Sun's wandering through the galaxy 4.5 billion years ago. That last possibility is the one that keeps astronomers up at night. If some fraction of the Oort cloud is made of material that originally formed around other stars, then the cloud is not just our solar system's archive, it is a sample of the galaxy itself. In 2017, an object called Oumuamua passed through the inner solar system. It was the first confirmed interstellar visitor ever observed. It came from another star, swung past the Sun, and left. In 2019, a second one, Comet 2I/Borisov, did the same thing. These objects came from somewhere outside our solar system. They were just passing through. Webb's observations have begun to raise a different question. If interstellar objects pass through our solar system regularly, as the models predict, how many of them get captured by the Sun's gravity? How many get trapped in the Oort cloud and stay there? Some models suggest the answer is significant. The cloud may be peppered with bodies that did not form in our solar system at all. They came from other stars, in other planetary systems, billions of years ago, and they have been sitting in the deep dark ever since. If that turns out to be true, and Webb's spectroscopy is increasingly suggesting that it might be, then every time a comet falls from the Oort cloud into our skies, there is a chance, however small, that we are looking at material from another world. This is not metaphor. It would be actual physical material, born in the gas clouds around another sun, drifting across hundreds of light years before being caught by our star. Think about what that means in practical terms. Right now, as you sit here watching this, somewhere in that dark sphere surrounding our sun, there are trillions of frozen objects drifting on orbits so slow that a single revolution takes more time than the entire history of life has occupied this planet. Most of them will never come close enough for us to study. But every so often, the gravity of a passing star, far beyond the orbit of Pluto, gives one of them a small nudge. And that nudge, over the course of millions of years, sends it falling toward the Sun. By the time the comet reaches our skies, the star that disturbed it has often moved on, may not even exist in the same form anymore. The visitor is the only evidence left of an interaction that happened in another era of the galaxy. I want to come back to one specific observation, because it is the one that, more than anything else, has reshaped how astronomers are thinking about this region. In 2023, Webb's NIRSPEC instrument captured a high-resolution spectrum of the gas surrounding Bernardinelli Bernstein. The team analyzing the data noticed something nobody had predicted. The carbon dioxide signature was strong, too strong, higher than the proportions seen in any comet from the Kuiper Belt, or any short-period comet ever studied in detail. What that means is still being debated. One possibility is that the Oort cloud objects formed in colder, more carbon-rich regions of the early solar system than we thought. Another is that they have been altered over billions of years by interstellar cosmic rays. A third is that the comet's outer crust has changed chemistry due to long exposure to galactic conditions. Each of these explanations rewrites part of our understanding of how the solar system assembled itself. And there is a fourth possibility, one that is harder to admit, but that some researchers have started to take seriously. The chemistry might be that different because the source population is more diverse than any single model can explain. The Oort cloud may be made of bodies that came from multiple regions, multiple processes, and possibly multiple stars. A patchwork, an archive built from many sources over the course of a galactic neighborhood's worth of time. This is what astronomers mean when they say the Oort cloud is not empty. They are not just confirming the math. They are saying the cloud has become a place with structure, history, and biography. A place that holds questions we did not know to ask, and answers we are only beginning to translate. What comes next is going to be slow. The objects Webb can study are limited to the ones that happen to be passing through ranges where the telescope can detect them. There is no way to point a camera at the Oort cloud as a whole. The distances are too vast, the signals too faint. But each year, more long-period comets are detected. Each year, Webb adds to a catalogue of spectra that, taken together, is starting to draw a map of a place we cannot visit. A statistical map, a chemical map, a map made not of pictures, but of fingerprints. The Vera C. Rubin Observatory in Chile, now scanning the southern sky every few nights, is expected to discover thousands of new long-period comets in the coming decade. Each one will be a candidate for Webb to study. By the early 2030s, astronomers expect to have a sample of Oort cloud objects large enough to start statistically characterizing the cloud's composition by region. We will be able to ask whether one hemisphere of the cloud is different from the other, whether the inner cloud is chemically distinct from the outer, whether there are clumps, voids, or anomalies in the distribution. We will be making maps of a place no human will ever physically reach. There is one more thing worth saying. Honestly, this is the part that gets to me. For most of human history, the Oort cloud was unimaginable. It was not a place, it was not even a hypothesis, it was nothing. Then it was a guess, then it was a name. Now, in the last few years, it has begun to be a region of study with named objects, measured chemistry, and a growing body of literature. James Webb did not give us a photograph of the Oort cloud. It will never give us a photograph of the Oort cloud. What it gave us is something stranger and ultimately more useful. It gave us a way of listening. Each comet that falls toward the sun is a voice from a place we will never visit, carrying information about the deep past of our solar system and possibly about other stars entirely. Webb is teaching us how to hear those voices, one at a time. The message coming back is simple. We are not alone in our own backyard. The space between us and the next star, the space we used to think of as a void, is full of structure, full of history, full of objects that have been waiting in the cold and the dark for the moment something would finally look hard enough to find them. The Oort cloud is not empty. We just had to build the telescope sensitive enough to prove it. Thanks for watching, and I'll see you in the next one.